This video is looking at P2.3. So it is the third section of the P2 module, and this section is called Forces in Action. And so basically this section is looking at just different examples of forces in very specific scenarios. So some of this section is for triple only. So the first bit of this video is going to be for all students for combined science, and then I will let you know when we're moving on to the triple only content. So if you're only doing combined science, you can stop the video. So the first bit of this is springs. Okay, springs is our first major topic here. And so what we're basically doing is we are connecting a spring to a fixed point and adding a weight, okay, to the end of it. And we're going to measure, compared to the spring before there was a weight added, how much it has been extended by. Okay, so X is extension. When we do this as a graph, as an experiment, what we get is, so we're plotting a graph of extension, which is in meters, against force in newtons. We get the most beautiful, perfect straight line we will nearly ever get in an experiment. So the gradient of this line is what we call the spring constant. So this graph shows us what is called Hooke's law. So Hooke's law is force is directly proportional to extension, provided the elastic limit is not exceeded. So for some materials, what we will get is we will get a graph that basically looks like this, okay, or curve. And at this point, it's basically stopped behaving elastically. Now, what I mean by the word elastic, which is a key word, is that when I remove the weight, it returns to its original shape. This is the opposite of plastic, which is when something has become permanently deformed. So when we're talking about what the effect of our forces are in this particular section, it's deformation. It's causing objects to change shape. So in this particular case, once you get to, it stops being a straight line, Hooke's law stops being obeyed, and it no longer is behaving elastically, it's then becoming plastic deformation. So if whilst we've got the straight line part of the graph, we can work out the gradient, and that is the spring constant. So we get the equation F equals Kx, where F is the force in newtons, K is the spring constant, and X is the extension. And I just want to be clear, it's the extension, not the original length. So you have to, if you have the original length there, you have to take that away if you're measuring the entire thing with a ruler. So the unit for spring constant, if I rearrange this, would be Newton per metre. And obviously it's okay to do that in centimetres as well. Now the other thing we can do from this graph is we've got a distance and we've got a force, so we can do work done. So work done by the spring is going to be just the area under this graph. So that is going to be half, because it's a triangle, times the force times the extension. So this is the first equation for elastic potential energy. And what we can also do is I can substitute in Hooke's law's equation into this to get rid of F, and then I can have a second equation for elastic potential energy, half kx squared. Okay, so those are our three equations linked to materials that we should be aware of. So if you're working out the spring constant, it's a gradient. If you're working out the elastic potential energy, it's the area under the graph. And remember, this point here, okay, when it stops behaving elastically, is called the elastic limit. So this bit of the graph here is elastic, this bit is plastic, if you get a full graph, like so. So they're very likely to ask you to analyse a graph or talk about the experiment and the way that you do that. Different materials as well have different force extension shapes. So just a few examples. So we've got a force extension graph. So for a material that is brittle, there is no plastic region at all. So this material, brittle, an example of that would be like glass. So glass, when you put a force on it, will extend a little bit, but then will just shatter if you go too far. In contrast to that, the shape of graph that we just talked about, where you get this kind of shape, this is a material that is ductile, which means when you can draw it out into a wire, an example of that would be copper. And lastly, an elastic band or something made out of rubber is technically what we call polymeric, which just means it's a polymer. So an example of that would be rubber or an elastic band has a shape that looks like this. And also, if I was to remove the weight from this, it would follow a different path back. So the unloading and loading curves would be different. Whereas if I remove the weight from something that's been ductile, so it would deform elastically up to this point, then would start to be plastically deformed. So if I remove the weight, it would be deformed and there's now be a permanent extension that I can't get rid of. So these are just different types of materials just to be familiar with. So main thing with this is to know the 3 types and to be able to recognise the shape of the graph. The next bit that is for everybody is coming away from springs is gravitational potential energy. And this is really just an extension of some other stuff that's in P2. So we have the equation for gravitational potential energy, which is mass times g times the height. So mass being in kilograms, g being the acceleration due to gravity or the acceleration or the gravitational field strength, which is 10 newtons per kilogram or meters per second squared. More accurately, it's 9.81, but in your exam, 10 is fine. And height is h is height in meters. So in other words, if I have an object and I take it from here to there, so I'm going to lift it up by a certain height, okay, then I am giving it additional gravitational potential energy. And if my object was to then fall, then that gravitational potential energy would be converted into some other form like kinetic energy or perhaps heat. So that is the gravitational potential. And you can link that to lots of other equations, such as, for example, power, because you could have gravitational potential energy divided by time, and you could link that like so. Okay, so that bit here, that is the only bit of this section which is for combined students. So if you're doing combined science, you can either rewatch that section again if any of that doesn't make sense, or you can move on and revise something else. Triple students, there's a little bit more for you. There are 2 extra topics that we need to talk about, which is moments and hydraulics. So moments are turning forces. That's all a moment is. So basically what we talk about when we're discussing moments is we have a pivot point, okay, and we have from some distance away from that pivot point a force. So we are interested in the perpendicular distance from the pivot. So a moment, the equation is force times the perpendicular distance from the pivot. So for example, if my pivot was here and my force was coming upwards, it's this distance that I would be interested in, not that one. So it's always perpendicular to the direction the force is acting. If, however, again in contrast, I had a force going this way, it would be that distance that I would be interested in. Okay, so just be aware of that. Now, the principle of moments is that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So this is called the principle of moments. Just so you know what this means, okay, sum of the clockwise equals sum of the anti-clockwise moments. When an object is balanced, so for example, if I've got a seesaw and I've got some 2 small people sitting on this side and 1 big fat person sitting on that side. So I've got the force and the distance from the pivot. The clockwise, if this is balanced, the clockwise moments, which are actually on this side, because going clockwise that way, back towards the pivot, so would be the 2 distances. So if I call this F1 and this F2, so F1, X1, which is the distance from the pivot to F1, and the distance to the other one would be equal to F3, which would be this slump force, and X3. So the sum, if I add up all the moments on one side, so this one plus this one, will equal all the moments on this side if it's balanced. And from that, I can then rearrange that and work out any of the distances or the moments. The other point just about moments, just to mention, is the unit is Newton times meters, because obviously force is in newtons and meters isn't perpendicular distances in meters. So that is moments. Obviously, this can be applied to any kind of situation of levers. So, for example, what you can get is when you have a lever, you can apply a force on one side as an effort, and you can shift a load on the other side. Now, there is a sort of extra equation here, which is called mechanical advantage. And mechanical advantage, and just to put this into context, if I have a pivot, like a ball here, for example, and I've got a big rock, okay, that's going to be my load, something I want to lift, and I'm going to put some effort in here. So I'm going to put a force. Okay, mechanical advantage is load divided by effort. Okay, and it's just a ratio. So as a lever, how effective is that lever at transmitting force? So it has no units, like I said, because it's a ratio, but that is what you would do for that kind of question. You can have the same thing with gears. Gears are also an example potentially of a force multiplier. And lastly, the last section, again for triple only, is hydraulics. Okay, so hydraulics use fluids, specifically specifically liquids, not gas. Gases is pneumatics, because gases can't be compressed. So what we're applying here is an equation from P1, which is pressure is force divided by area. So if I have a piston at this point here, obviously this piston will have an area and it will have a force applied to it, and this piston over here has a different area and a different force that is going to be coming out. Now, because fluids can't be compressed, the pressure here at point 1 and the pressure here at point 2 have to be equal to each other. And so what that means is force 1 over area 1 will be equal to force 2 over area 2. And so I can rearrange that again to work out like the final force that's transmitted by my hydraulic system, or to work out like the area. So I can rearrange this equation accordingly. That's all that we need to really know about hydraulics. Also, I'll just mention the unit for pressure is the Pascal, or Newton per meter squared. So area is in meters squared, and force is in newtons. When you use this equation, it doesn't actually matter what the unit is for area as long as it's consistent. So you could do this in centimeters squared for each one as long as they're both centimeters squared. So that's a summary of P2.3. So this half, just to reiterate, is for combined science, and this half is for triple science as an additional information. So springs, gravitational potential energy and weight, moments, and hydraulics.